Before we get into our lesson today, let's make sure we're familiar with some old stuff that we're going to need for our lesson today. And we're going to start by talking about continuity, whether something is continuous. And so before we get into this problem, let's just remember that our definition of continuous is that there's no break. So the definition, if something is continuous at x equals a, so there's some a value where something's continuous. In order for something to be continuous, the limit from the left, that means as you get really close to a from the left side, so the limit as x approaches a from the left side of some function has to be the same as the limit as x approaches a from the right side. So what happens when you get close to a from the right side? So the limit as x approaches a from the right side, those need to be the same as each other. And the limit is just about what happens when you get really close, not what's actually at a. At a, we need that value to be the same as what you're getting close to from the left and the right. And so we need three things to all be true. The limit from the left is the same as the limit from the right, which is the same as the function value at a. So is f of x continuous at x equals 3? Well, we have two separate functions. If we had picked any other number, like if we had picked x equals 1, the answer is yes, of course it's continuous because linear functions don't have any breaks, quadratics don't have any breaks. But at 3, we're switching over from one function to another. And so we need to know, is it continuous? And you need to be able to justify your answer. So is it continuous? And what's the correct justification you need here? This would be on the free response portion, and you'd need to be able to justify. So let's see. Well, to justify, we need to do the limit as x approaches 3 from the left. And so we're going to be looking when x is less than 3. And we're going to find this limit by doing just direct substitution. So of f of x is called f of x is equal to, when I just plug in 3, it's 2 times 3 is 6, plus 2 is 8. Okay? F of 3, I also need to be the same, and f of 3 is when it's equal to 3, and that's going to be the or equals to part. And so I'm going to plug in 3 here. 3 squared is 9. 9 minus 1 is 8. It's not about what happens when we get close to it. It's about what happens when we actually are at 3. And we also need the limit as x approaches 3 from the right. So when x approaches 3 from the right, we're talking about what happens when x is greater than 3. So when x is greater than 3, we'll use this function. And as we get really close, we've found that we can do direct substitution. And so we'll get the same answer as we did for the or equals to part. So the answer is, let's answer this question. It's a yes or no question. Is f of x continuous? Yes. And the justification is because the limit as x approaches 3 from the left of f of x equals f of 3 equals the limit as x approaches 3 from the right of f of x. This is what you need to get the points on the AP exam. This actually doesn't need to be shown, but this does need to be shown. This justification is what's important there. Okay, let's see how well you remember the limit definition of the derivative of f of x. What is the limit definition of the derivative of f of x? F prime of x is equal to, and hopefully we remember that this is the one that is the limit as h goes to 0 of f of x plus h minus f of x over h. If you do not remember this, if you didn't remember it, this is a great time to go back and make sure you remember it. We've got our final exam coming up in not very long. This is definitely a thing you want to remember, is what is the definition using the limit. We're actually going to do something cool with this soon. So let's make sure we know it. But it involves limits, right? So both the justification for continuity involves limits, and the limit definition of a derivative, which, in case you don't remember, is, so it's like saying, look, here's a point x comma f of x. We can pick another point very nearby by going h away. So this is x plus h. And the new point will be f of x plus h. And so what we're doing is y2 minus y1 over x2 minus x1, and x plus h minus x gives you just h. So this is y2 minus y1 over x2 minus x1, and we're letting h go to 0, which means these points we'll be getting right on top of each other. So with that in mind, we're going to start our new unit talking about differentiability. And this word The English should be clear, but, if English is not your strong suit, that's okay. Differentiable means, can you do the derivative? Is it possible to differentiate? Is the derivative defined? So another way of saying this is f prime of a defined? So remember that the derivative function tells us what about the tangent lines? So the derivative of a function tells us the slopes of the tangent lines to a function. And the formal definition of the derivative that we just looked at, the definition of the derivative involved limits. And specifically limits from the left and the right. For a limit to exist, what has to be true for the limit to exist? So for the limit as x approaches a of f of x to exist, we need that the limit from the left is equal to the limit from the right of f of x. If it's coming to the same thing from both sides, we say the overall limit exists. And so for the derivative to exist, the limit from the left and the limit from the right of this need to exist. The limit from the left and the limit from the right need to exist. So when we have a piecewise function, to tell if a derivative exists, hold on, where's my thing? Okay. When we have a piecewise function, let's see where you guys are at on this. Determine each of the following. What is f of 0? And f of 0 just means this isn't about a slope. There's no limit here. It's just when x is 0, what's the y? And so this says we use this rule when x is to the left of 2, and we use this rule when x is greater than 2. 0 is less than 2, and so we use this top rule. So it's 0 squared plus 1, which is 1. So f of 0 is 1 when x is 0, y is 1. What about f of 5? F of 5, well, we need to use, this is a piecewise function. It tells us when to use each rule. We use the top rule when x is less than 2, and the bottom rule when x is greater than 2. 5 is greater than 2, so we use the bottom rule. So it's 4 times 5 minus 3, which is 17. F of 2, well, we need to use the top rule here because it's less than or equal to 2. So when x is equal to 2, we use the top rule. And so it's 2 squared plus 1, which is 5. How about f of negative 1? When x is negative 1, x is less than 2, so we'll use this top rule. Negative 1 squared plus 1. A negative times a negative is a positive, so positive 1 plus 1 is 2. Ooh, what about f prime of 0? This is different. So f prime of 0 is asking you what is the slope at x equals 0. Well, when x equals 0, this is the rule we're using. And so we can set up a derivative function. We can say, look, this is a formula for the y value. We can also set up a formula for the derivative. The derivative is going to be the derivative of this one when we are to the left of 2, and the derivative of this one when x is to the right of 2. Now, there is something very slightly different than how I wrote these rules here. So I did the derivative of the top one when x is less than 2, and the derivative of the bottom one when x is greater than 2. So that should be clear. But there's something you may have noticed, which is that in this one it had less than or equal to, and in this one it has greater than. But in this one I didn't put equals to on the top one, and I'll explain that in just a second. So what is f prime of 0? Well, the derivative at 0 is going to use this rule because the derivative is 2x when x is to the left of 2. We'll be doing the slope of this one when we're to the left of 2. And so the slope here is 0. 2 times 0 is 0. How about f prime of 5? What's f prime of 5 equal to? Well, when x is 5, 5 is greater than 2, so we'll need to use this rule. And this rule says that the slope is always 4. So as long as we're to the right of 2, the slope will be 4. And that should make sense because it's just a linear function. The slope will always be 4 there. F prime of negative 2. This isn't 2, it's negative 2. So negative 2 is to the left of 2. So we'll be doing the slope of this one. And so 2 times -2 is -4. Is the function continuous at x equals 2? Go ahead and answer that on your own and make sure you're able to justify your answer. So is the function continuous at 2? Well, the way you should have been able to justify your answer is that when you do the limit as x, you have to use limits here. The limit as x approaches 2 from the left of f of x. So when x is coming in from the left side, we'll use this rule, which will be 2 squared plus 1 is 5. That's equal to f of 2 because it's the same rule. So when we plug in 2, we'll use this rule also. So this is also 5. Oh, sorry, I should put equals f of 2. And it's also, well, let's see if it's equal to. We need to see if it's equal to the limit as x approaches 2 from the right. As x approaches 2 from the right, we'll have to use the rule for when x is to the right of 2. We can do it with direct substitution. 4 times 2 minus 3 is also 5, which is the limit as x approaches 2 from the right of f of x. So at 2, the limit from the left and the limit from the right and the function value are all the same. And so yes, because the limit as x approaches 2 from the left is equal to f of 2, which is equal to the limit as x approaches 2 from the right. So since all three of those are equal, the function is continuous. Now, is the function differentiable? Let's think about what it means for a function to be differentiable. To be differentiable for a function, we need to be able to take the derivative. And let me start by saying, if there is a break in the function, if the function is not continuous, it's not differentiable. What's the derivative here? Is it this one or is it this one? Well, the answer is we don't know because there's a break, and so it's not defined. So if a function is not continuous, the derivative is not defined. We just proved that it was continuous at x equals 2, so that's not the situation. But just because it's continuous does not mean it's differentiable. Remember, the limit definition of the derivative involved the limit, which means it's both the limit as h approaches 0 from the left, and that needs to be the same as the limit as h approaches 0 from the right. The derivative from both the left and the right must be the same in order for the derivative to exist. And in this case, actually, the derivative would not exist because the derivative from the left is negative and the derivative from the right is positive. What we need to do is see, is the limit as x approaches 2 from the left of the derivative equal to the limit as x approaches 2 from the right of the derivative. Is the derivative the same from both sides? And we can do that just by plugging in. We can put in 2. So direct substitution, we get 4 equals 4. And so it is differentiable. And here's how we justify. We say yes, because there are two things that need to happen for a function to be differentiable. Yes, because f is continuous. That's the first thing. The function needs to be continuous. We already proved that over here. And the limit as x approaches 2 from the left of f prime of x is equal to the limit as x approaches 2 from the right of f prime of x. So the slope is the same from both sides, therefore, and the function's continuous, therefore it's differentiable. Let me show you what a graph of what this function we've been dealing with looks like, and we can see why it's differentiable. This function was a quadratic to the left of 2, so it was a quadratic. And then at 2, it switches over and becomes linear. It's this function 4x. This is y equals 4x plus 3. This one is y equals x squared plus 1. And it switches at x equals 2. And you can see it meets up. That makes it continuous. The limit from the left and the limit from the right of f of x was the same and was equal to f of 2. And notice the slope coming in from the left is 4. And the slope on the other side is 4. There's no change in direction of the slope. And so this function is differentiable. Let's look at another function. Here's f of x. I want you to determine on your own if f of x is continuous and pause to see if you can justify your answer well. You need to be able to do it and write it correctly to get the points on the AP exam. Is f of x continuous? Well, what do we need to check? We need the limit as x approaches 1 from the left of f of x to be equal to f of 1 to be equal to the limit as x approaches 1 from the right of f of x. So we need it to meet up. And let's see, the rule on the left side is going to be, we'll just do direct substitution here. So it's 1 minus 3 plus 1, that's negative 1. F of 1 will be the same rule. What about the limit as x approaches 1 from the right? Well, when we're coming in from the right side, we need to use this. This is when x is bigger than 1, we use this rule. So we need to substitute in 1 for here. And so we need to see, is it equal to 1 minus 2? And these are all the same. They're all negative 1. So the answer is the function continuous? Yes, because the limit as x approaches 1 from the left of f of x is equal to f of 1 is equal to the limit as x approaches 1 from the right of f of x. We want to feel comfortable being able to write this justification. This is what is needed to get the points on the AP exam. Now you get to try this new thing. Is f of x differentiable at x equals 1? Does the derivative exist at x equals 1? Actually, before we move on to that, guys, let's look at a picture of what was happening here. This is this graph. It was this cubic function. So this was part of a cubic function when x is to the left of 1, and then it became this parabola when x is to the right of 1. So here's when x is 1, and we can see that it met up. The function, the value from the left and the value from the right were both getting close to negative 1. And so it's continuous. Now, is it differentiable? Well, to be differentiable, what are the things that need to happen? We need it to be continuous. Was it continuous? So continuous? Yes, we already checked up above. It was continuous. The other thing is we need the limit as x approaches 1 from the left of f prime of x to be equal to, and I'm going to put a question here because we have to check it, to the limit as x approaches 1 from the right of f prime of x. So I need the slope as I'm coming in from the left to be the same as the slope as I'm coming in from the right. How do we do that? Well, here's our function. To find the slope from the left, we'll just do the slope of this one. So f prime of x is equal to the slope when we're left of 1 is going to be the derivative of this. 3x squared minus 6x plus 1, that's the derivative of this. That's when x is less than 1. When we're to the right of 1, we need the slope of the one that's to the right of 1. So 2x minus 2. And notice I have not put or equals to here because I don't know if the derivative exists at x equals 1 or not. I need to make sure these limits from the left and the right are the same. So the limit as x approaches 1 from the left is 3 minus 6 plus 1, which is negative 2. The limit as x approaches 1 from the right is 2 minus 2, which is 0. These are not equal to each other. And we can see it here. The slope coming in from the left was negative 2. The slope coming in from the right is 0. And because they meet, this is called a cusp. When it meets at a place where the slope coming in from one side is not the same, it's like a hard angle. It's not a smooth curve. It's like a hard angle. It is not differentiable because the slope from the left, the limit of the derivative as x approaches a from the left, does not equal the limit of the derivative as x approaches a from the right side. This is called a cusp when the slopes aren't the same from both sides. And so what's the slope at this point? Well, it's undefined because the limit from both sides wasn't the same. So the overall limit doesn't exist. And so this definition falls apart because the limit from the left does not equal the limit from the right. And so there is no derivative there. And so we say, let's answer the question, is this function differentiable? No, because the limit as x approaches 1 from the left of the derivative, the limit of the derivative as x approaches 1 from the left, did not equal the limit as x approaches 1 from the right of f prime of x. If I were going to be saying yes, I would need to prove that this is true and also proved that the function was continuous. This function was continuous, but it didn't meet the two things it needed. It needed to be continuous and have the slopes be the same from the left and the right, and it wasn't. And so this is a function that is continuous but not differentiable. If a function is differentiable, like this one is, it must also be continuous. So we say if something is differentiable, then it's automatically continuous. But a function being continuous does not automatically make something differentiable. It is differentiable. If a function is continuous, it's differentiable if the limit as x approaches a from the left of the derivative is equal to the limit as x approaches a from the right of the derivative. It's got to have that additional thing. If the limit as x approaches a from the left of the derivative does not equal the limit as x approaches a from the right of the derivative, then it's not differentiable. On the other hand, if something is not continuous, it is automatically not differentiable. So this is kind of like the three-dimensionable. If a function is differentiable, automatically continuous. If a function is not continuous, it is not differentiable. But if a function is continuous, it might be differentiable. We need to check and see if the slopes are the same from both sides. So let's practice this. Let's see how this goes. I want to give you guys one more example problem to try on your own to see could you get this right, and then we'll move on to new things. Okay, consider f of x equals x to the 1/3 power. Find f prime of x. Go ahead and do that on your own, and you can leave it unsimplified as a power if this one was a power. So f prime of x, this is a power rule, this is x to a power. We multiply by the power, and we lower the power by 1. So lowering by 1 is the same as lowering by 3/3. So this is -1. So we get -2/3. So here is the derivative. Now I'm going to rewrite this and simplify it. This is 1/3. It's a negative exponent, so it's in the denominator. This is the cube root of x squared. So this is how we write it. Where is the derivative undefined? What value of x, so at x equals what, would make this derivative undefined? Well, just like with function values, if you have a formula, the derivative would not be defined if the derivative formula is undefined, right? So we are not allowed to divide by 0. And so if the denominator is 0, that would be a problem. And that's what happens here. When x equals 0, the denominator would be 0. And so this would be an undefined value. At x equals 0, f prime of x is undefined because it makes the denominator 0. And we say this by saying f is not differentiable at x equals 0. Remember, differentiable means the derivative is defined, or you can do the derivative at that point. We cannot do the derivative at x equals 0 because when we try to plug in 0, it's undefined. This function is differentiable at all other values. Okay? Why don't you guys try this one on your own? Find f prime of x. And hopefully you realize you need to do the quotient rule because it's a quotient, it's dividing. So we have to do, the derivative is going to be the derivative of the top times the bottom left alone, minus, we leave the top alone, times the derivative of the bottom, which is just 1, all over the bottom squared. And I'm going to go ahead and simplify the top. This is 6x squared minus 24x minus 3x squared, the bottom squared, and these terms can simplify. They can combine, sorry. 3x squared minus 24x over x minus 4 squared. So where is f prime of x undefined? F prime of x is undefined when x equals 4. Because when we put in 4, we'll get something over 0 and the derivative will not be defined. Now, none of this was necessary to tell that at x equals 4, this function was not differentiable. So not differentiable at x equals 4. But I didn't actually need to find the derivative formula to see that it was not differentiable at x equals 4, because at x equals 4, the function wasn't defined. And if the function isn't defined, it's not continuous at x equals 4. And if it's not continuous, remember, it's automatically not differentiable. It has to be continuous in order to be differentiable. It also has to be some other things. But if you see that a function is not continuous, you automatically know it's not differentiable. So if a function is not continuous, it's automatically not differentiable. So f prime of x is undefined at x equals 4. We say this function is not differentiable at x equals 4. In this case, the derivative was undefined because the function was not continuous at x equals 4. The function wasn't continuous. And if the function isn't continuous, then it won't be differentiable. Now you'll notice if we had actually done the limit as x approaches 4 from the left of the derivative, and we had tried to see is it equal to the limit as x approaches 4 from the right of the derivative, from both sides, it actually comes out to be the same thing. It goes to positive infinity. So it goes to positive infinity, but these are a type of not existing. Neither of the limits exists. And they don't exist because there's an asymptote here. So at x equals 4, there was an asymptote. So that's what's going on. All right, guys. F is not differentiable at x equals a if either one of the following is true. So it's not differentiable if f is not continuous at x equals a, or the limit as x approaches a from the left of the derivative is not equal to the limit as x approaches a from the right of f of x. Oh, f prime of x, sorry. So there's two things that have to be true, and if either one of them is not true, it's not differentiable. The function has to be continuous, it has to meet up, but also the limit from the left and the limit from the right must be the same. And here, this function would not be differentiable because the limit from the left is positive and the limit from the right is like 0, and so they wouldn't meet up. Find the derivative for each. Determine where the function is differentiable. And some of them might be differentiable everywhere. So this function, what's the derivative? Hopefully we realize f prime of x is 2/3 times x to the, we need to lower the power by 1, negative 1/3 power. This can be simplified to 2/3 cube root of x. And so because of this, the function is not differentiable when the denominator is 0. So not differentiable at x equals 0. And that's because when we try to plug in 0, the derivative will not exist. How about this next one? What's the derivative? Oh, sorry, 6x squared plus 6x. So where is this not differentiable? Well, it's differentiable everywhere. We have a formula for the derivative, and there is no place where this function will be undefined. Some kids sometimes say, like,